Welcome back to the Math Professors. If you enjoy content that can be found in any college math class, please consider liking, subscribing, and sharing. So, in a previous video, we showed the derivative of e to the x was equal to e to the x using its Maclaurin series, or its Taylor series centered at 0. And I just showed the work here. We know that when we take the derivative with respect to x, we really only have to worry about this x term. The n factorial really is a constant in this case. So, bring the power down, drop it by 1. Rewrite the factorial. Remember that the index will now go to 1 as opposed to 0. When you re-index it, you do get e to the x. Now I want to do something similar for the indefinite integral of e to the x. So really kind of the goal is, if I want to find the integral of e to the x dx, we know that this is going to be equal to the integral of the summation from n equals 0 to infinity of x to the n all over n factorial. Now we have to be careful with integration because this, what I want to do is I want to integrate this thing, so I really want to take this integral inside the summation, but it'll only work if it's a convergent series. So I have to test convergence of this, and let's do that real fast. So what I'm going to do is verify convergence through, well, the way it's done, it's the limit as n goes to infinity of the absolute value of a to the n plus 1 all over a to the n. And I just have to verify, that this thing is going to be equal to less than 1. That'll give us our interval of convergence. So a to the n plus 1 is going to be, everywhere there's an n, now there's an n plus 1. This is our a to the n. So this is going to be equal to x to the n plus 1 all over n factorial, divided by x to the n over, n plus 1 factorial. So everywhere there's an n plus 1. And then divided by the original absolute value. Now what we're going to do is I'm going to rewrite this by multiplying by its reciprocal, and also rewriting this x to the n plus 1 as x to the n times x, and rewriting the n plus 1 factorial, similar that I did over here, is going to be n plus 1 times n factorial. And then when we multiply by the reciprocal, we're going to have an n factorial here, and divided by x to the n. Now we can see that the n factorials will cancel, x to the n will factorial, x to the n will factor, and now remember this is the limit as n approaches infinity, so I can pull out the x because it's a constant with respect to this limit, and this is going to be equal to the limit as n goes to infinity of 1 over n plus 1. I can drop the absolute values because we know that n is going to be positive. And, this limit is equal to 0, so this thing is equal to 0, which is always less than 1. So that means the interval of convergence is going to be minus infinity to infinity, really verifying that this is a convergence series. So since it's a convergent series, what this allows me to do is interchange the summation of this integral. Now, I do something very similar. I'm going to add 1 to that power, divide by this. So now this is going to be the summation n equals 0 to infinity of x to the n plus 1 all over n plus 1, and then we're going to have an n factorial. Now, I know it doesn't look really the same, but this is going to be an n plus 1 factorial, but remember that really when, remembering that they're not exactly the same because of this plus c part, that really the indefinite integral and the original function really must just differ by a constant, and that's really what we have here. So this is going to be n plus 1, and then the bottom is going to be n plus 1 factorial plus c. Now what we know is when we plug in n equals 1, this is going to, n equals 0, this is going to be x all over, 1. And then plus we're going to have x squared over 2 factorial plus x cubed over 3 factorial plus, and so on. And what we know is this original Taylor series actually has 1 plus x plus this. So it's really missing this 1, but since this has this plus c, that these things really only differ by a constant. So we can see that this is, still e to the x plus c. So again, if you like the content, please subscribe.